Let's wait just a moment right now. Yeah. Okay, now it's time to start, I think. I'd like to welcome everybody in this very exciting lecture on how to combine LLMs and small data learning so that we have more reliable learning. I would welcome Professor Gong to deliver this lecture. He has done his PhD degree at Oxford University, and he is now at the Queen Mary University of London, where he works on machine learning and computer vision. So, Professor Gong, now the floor is yours.
Thank you, Yanis. Good afternoon. Hi, everybody. So I'm going to talk about more reliable small data learning, exploring large foundation models. I think over the last decades, the computer vision community and in a broader sense, machine learning community have been asking ourselves the questions, and one of the most common questions is, where are my labels? And increasingly, we realized in large-scale deep learning, annotation probably is not scalable, particularly now increasingly in videos. And also annotations are inconsistent, and often different labels are assigned to the same objects across different domains, so they're not transferable across different domains or data sets. And often annotations are also subjective. In other words, they are biased, either because of mistakes or because of subjective interpretation. So increasingly, there's a demand and also necessity for self-supervised learning. And particularly, I'm going to talk a little bit about today is the sense of training-free test time inference. So in other words, what if we don't have annotations on data? The second set of questions now increasingly become critical is, where are my data? So over the last decades, we started with not enough data, and then we have lots of centralized big data. Now, due to increasing demand for privacy and transparency concerns, we have more decentralized, smaller data in access. And we have more imbalanced data in training, again, due to factors that we don't have any control on, so they'll have bias in sampling. And also limited data in processing because of the computer energy resource capacity limitations. So increasingly, I think there's a shift from very large scale centralized data and towards how do we explore perhaps smaller, decentralized and distributed data and the learning capacity. So in this context, I would use an example to illustrate some recent development on few-shot image generation, particularly discuss about the need and exploration for generative distribution diversity. So the work I'm going to talk about are in two sets. The first, training-free test time inference, and particularly self-supervised learning of prompt control in image segmentation. And based on two pieces of work, my students and myself and some colleagues collaborated on this year's AAAI and also next week's Neural Lips. And then I'm going to talk a little bit about generative distribution diversity and use an example from this year's ECCV work on few-shot image generation. So first example is self-supervised learning of prompt control in segmentation. In particularly, I'm going to introduce a model we developed called GenSAM, generative SAM. SAM was initially proposed by Facebook, segment anything model. And particularly in this context, we're trying to apply this idea to segmenting camouflaged object. So what is generative segmenting anything model? The idea is that at the test time, we perform instance segmentation of very challenging objects that are typically camouflaged objects without model training and free of manual prompting, neither visual nor textual prompting. So here's some examples, and say starting with different animals. Those actually on the seabed, different sea animals, and also insects on the tree, and also some other objects. So you can say that the visual differences between object and background context are visually very vague and non-distinct. So let's go back a little bit on SAM model, which was proposed, I think, over 2.5 years ago by Facebook. It stands for Segment Anything Model. It's a model requires a manual visual prompt in the form of a user needs to interactively define points. So those points, for example, here, I hope you can see my mouse movement. So you can see the points. Let me see whether I can get a pointer. Oh, it's not straightforward. That's not bother. Hopefully you can see my mouse.
Your pointer is visible.
Okay, thanks. So you can see using the original SAM model requires you to give visual points, both for foreground and also for background. So essentially, a user needs to interactively initialize where are the foregrounds and where are the backgrounds. Obviously, the more points you give, the model performs better. But with 1 point in foreground and background, model can be initialized. Since SAM appeared, that it caused a lot of interest and potentially has lots of potential applications. So people are trying to look at it and then find out this assumption is quite restrictive, because for certain objects, for example, here are some examples, it's even difficult for the human eyes to differentiate where are the foreground and where are the background. So it's a bit of a catch-22 problem. And the whole idea is whether the model can tell us how to segment foreground, background in a camouflaged object, where if you require a human to tell the model where to start, and that sometimes is probably not tractable. And so there are efforts trying to improve the original SAM model. And for example, using Scrabble, also define structures rather than just a point. But again, requires visual prompt, using human to define the main structure of the foreground, and then enable the model to initiate better. And further, there are ideas of introducing text prompt. So for example, using this model called clip surgery, is actually trying to using both visual prompt in the form of points and also text prompt. But text prompt needs to be very carefully designed. They are per image instance specific. So our research questions are, how do we remove both the visual prompt and also remove instance specific text prompt. And because prompt engineering to make a very accurate or very relevant text prompt for each image is very challenging, as we find out later. And so the objective here is, can we design a model that can start with a generic prompt for all the images in a particular domain? So a single generic prompt, and then the model learns by itself to discover what are the appropriate prompt without any visual points being interactively imposed upon by a user. So that's the context of the work. So here's some examples of using different derivatives of SAM, using original and Scrabble, and also using clip surgery and using generative SAM as the model we present here. So these are the two examples, and we'll show some other examples later. And you can see it's actually very challenging if you use just using single points, because there are camouflaged objects which are very similar to the surrounding context. So the model doesn't actually work. And in this case, also doesn't work. Using Scrabble, actually it does better. Using text-specific, instance-specific text prompt with points doesn't work very well either. And here's the generative SAM model. So a generative SAM model is a multi-model auto-prompt control method. So it contains a couple of building blocks. And first, it has a mask generation. So the mask is in the visual space. So for segmentation, typically you need generating a mask at pixel-wise level to differentiate foreground instances from a background. So this model doesn't require any training. So it's at the test time instance segmentation, and it generates iteratively, we call it progressive, masks in a cycle. So here's an illustrating of, so it generates hypothesis and then invokes SAM to generate a mask, and then using the mask coming back and to test the hypothesis. I'll give you more detail about how the hypotheses are set. So in terms of the data flow, it starts with image to capture model using a BLIP2 and generates hypotheses. We call them keywords of plausible foreground and background. So there are multi hypotheses of foreground and the background. And then goes through an iterate multiple chain of sorts reasoning, and then come back to regenerates the mask and goes through that loop again. So here's a bit more detail. So the second part of the model, we call it automated instance-specific consensus prompting. In other words, you can say from here, if you've taken the image input, so we're trying to perform a segmentation. It's visually very difficult to tell where is the foreground and the background. So the prompt, which is given as a caption, say a large grasshopper is sitting on the ground. So that's a starting point. So using the clip, it generates multiple hypotheses. So those are all different hypotheses and answers, and then using a clip to generate a heat map for each of the hypothesis and answer. And the heat map, which is a clip attention map, then generates another set of, so this is answer a set of questions, generate another set of hypotheses and as the background. So this is the foreground and this is the background. So we generate multiple hypotheses as a foreground and its corresponding background. And so in other words, it's trying to reason about what is plausible. with multiple hypotheses, both foreground and the background. And the processes, we're using BLIP2 as a caption model to generate those keywords and background. And we're using CLIP to generate visual heat map. So this is the foreground heat map, and this is the background heat map. So once we have those, we go through this a loop, and this loop invoke another foundation model. Here we actually uses a NAMA model. We tested both CLIP and ChatGPT and NAMA, but we use a NAMA model here to generate a expanded prompt. And this prompt is different from the original starting point. The starting point is a very generic, and this one generating something specific given the heat map or visual alignment, both in foreground and the background. And this model generates a new prompt and goes through this loop again. So here's illustrate this loop going through multiple times. And when the heat maps are generated in foreground and background, those are fed into as hypothesis for visual points for the SAM. So the SAM is generating masks. So these masks then recycle. So this process iterates multiple times, where SAM simultaneously getting a refined heat map iteratively to generate a mask. And so the masks are also iteratively generated. So this is an initial design we have. So and trying to explore essentially 3 different components. One of them is using a caption model to generating hypothesis in foreground and background, and then using a visual alignment model. In fact, CLIP is a poor alignment model because CLIP doesn't actually understand spatial grounding. In other words, the heat map are approximation. To provide both the semantic and the visual sequencing alignment. So using this as input to generate a feed into another large language model to generate iteratively and a refined prompt. So from a very generic prompt to go to specific, each image instances have a different potential different object with different background. And the model would converge into different hypotheses and a different convergence. And simultaneously, each of those heat map, a combined foreground and background heat map, will generate, as if you like, approximation for points into a SAM model. So the model here is focused on generating those hypotheses, where the SAM model is taking as a mechanism to generate masks. So more details on how internally the model is built. So we have actually multi-channel of attention blocks, and it's iteratively refined, and there will be more details in the AAA papers. So I move on to the next. So experiments for camouflaged object. There are 3 data sets currently being commonly used. You can see just here some examples. Those are insects in forests or in vegetation environment. Here's some objects, both underwater sea animals and also some other. So you can see the objects are very similar to the surrounding environment, and it's difficult to tell. For example, this particular object, I visually found it difficult, and here as well, I actually can't tell if you're using your eye to differentiate. And here's another different type of object. So they're all visually very non-distinct. So here are some test results for using the model. So you can say how the model generates a heat map and how the heat maps are evolving over time across different iterations, and both the foreground and the generating, those are the actually points approximated by the heat map attention. And here's the ground truth, and here's the converged output in the form of a mask. So this is over 6 different iterations. Here's another example. Here's the ground truth. Here's the image input. And here's the model's estimation of heat map generated points using prompt control. So it generates different prompt iteratively to hypothesis where the points might be. And then as a result, it drives the mask generation to create the final results. Some evaluations. So the model performs well for all these 3 different data sets. And so here's a better way of visualize this. So those are the error, mean absolute error. Those are the annotation quantity. In other words, how much specific text prompt you need to specify. So Scrabble is actually quite expensive in terms of annotation required. So less annotation is better in this exercise, and less error on this exercise is better. So this gives a comparison of different methods. Those using Scrabble as a visual prompt actually doesn't do as well, and with a lot of error. Using actual clip surgery with prompt, it generates a lot of error as well, because the prompt engineering becomes really challenging, and it's difficult to generate an optimal prompt for each individual image. So build on that, we developed a new model to expand further on prompt control for segmentation. So this is a work to be presented next week at NeurIPS. And it's how to leverage hallucinations to reduce manual prompt dependency. So we call it ProMac, prompt mask cycle generation. So here's an example of how the model is trying to perform. So these are the inputs. So here are 4 different examples, and it generates, I hope you can see the bottom here. So it generates predictions over iterations and diffusion. It actually generates diffusions, synthesized explanation. Let's say it comes back again. And you can see different iterations generate different prediction of potentially where the object masks are. You can say it changes starting from the beginning, and then here's the final model output, and here's the ground truth, and compare with GenSam I just described, and it had okay, it comes back again. So you can see it's the first iteration. You can see it's actually quite uncertain, and then improves, and each iteration improves further, and the prediction. So there are 2 components. Again, there's a semantic interpretation and there's a visual alignment. And if you compare with GenSam, it improves on some of the more difficult objects. Now, so since the beginning of the year, over this year, there are a couple of models. The GenSam, the model I just described, but there's another model called grounded SAM, has been proposed trying to address the problems just described. So here, a number of methods have been using, for example, Grandino, which is another alternative capture model similar to BIP2, but it actually has a slightly better performance. And also, so there's a work proposed using Grandino to generating initialized hypothesis with captions. So in the same spirit as how we use the BIP2, and then using this to generate a prompt in the sense of keywords, and then use that to iteratively generate a mask. So in a very similar spirit to Jensen, as we just described. And the differences here is Grandino actually enable you to generate open vocabulary. So in a way, it's trying to generalize to objects which are not trained, whereas in Jensen is not requiring any training. So both of them are open vocabulary based models. However, there are difficulties, including JSON and also grounded SAM, because they use a large language model. In JSON case, a NAMA model, it generates a lot of hallucinations. So once you generate hallucination, the model doesn't necessarily always converge into the right object class. It actually sometimes generates lots of objects which didn't exist in the images because of hallucination. So one of the key problems is how do we actually address this problem of hallucination? The existing work in the broader context, most of the community currently is thinking about large language models or large multimodal foundation models. Hallucinations are considered to be detrimental. And so methods are developed trying to minimize or remove them. But we consider that's not the case in lots of potential problems that we're trying to solve. So we argue differently. We consider hallucinations are actually good for exploring knowledge, and because there are essentially hypotheses learned from pre-training, foundation model pre-training, so they provide a richer context for iterative test time inference, and particularly they enable self-supervised learning of prompt control in context, and we call them meta-prompting. So in this extension or this piece of work, we consider how to utilize hallucination rather than how to remove hallucination. So we actually use it. For example, show some examples. So if we take an original image, in fact, there's an animal here. Visually, it's very difficult to say. But if you block the area where the animal is in the image, and what you ended up with is the context. So in this instance, it's a hay field. So in the middle of the haze, there's a potential animal. But the models, the actual large foundation models, understand in that environment, there are a whole bunch of animals are all possible. For example, lion, leopard, and so on. And instead of considering them a noise, we should consider them, they are all plausible possibilities. And then the task of a model is trying to validate which is more true. So this part, it's another example illustrate to how do we use this to perform and more accurately optimizing a prompt. So this is the original image. And the way how do we try to generalize this idea is we divide images into, so this example is divided into quarters. But in general, what you do is you randomly divide it into multiple parts. So in that process, some of those parts would contain a possible object, or contains no object, or contain a part of object. And the whole idea is that you randomly generate a lot of visual compositions from the original image. And those visual compositions then are used for the foundation models to generating plausible hallucinations. So some of them contain the object you are interested in trying to segment. Some of them contains no object, but just having the contextual surrounding scene. And some of them have a bit of the object, but you have no knowledge how that's being divided. And by doing that, we trying to create a process to perform a reasoning. So the model contains three components. One is a prompt generator. Another one is a mask generator. Another one is a visual contrastive reasoning module. So this has some similarity to GenSam. The main thing is the visual contrastive reasoning is different, and also the way how we generate those prompting is computed differently. So here we're actually generating a ranking list of all plausibles, and then we actually compute a score for the ranking list, and we change the ranking list. So it's essentially all hypotheses, all hallucinations are considered to be valid hypotheses, and then we rank them, and we generate a score based on how they align with the visual components. And also the visual input are randomly divided into multiple compositions in order to generate this score. And by doing that, the model generates a lot of hypotheses, you could say hallucinations, and then converge onto the few and to the correct one eventually. So it's an iterative, the overall objective, it's iteratively generating masks, and I use the mask. So the masks are the visual space feature representation to guide a prompt generator. So that's a text prompt generator to self-learn a better prompt by jointly optimizing alignment between the prompt and the mask. So there are two iterations. For example, here, starting with an initial instance prompt, which could be a generic, in this instance, it could be generic prompt, and then you're generating a mask. And so the mask is generated, and then you use the mask to generating a prompt. And so the mask, essentially, this is similar to the GenSam, but then this is going back to align with the visual features and trying to say whether they actually agree. So iteratively, you have the visual prompt and going to the text prompt, and the text prompt come back to the visual prompt, and vice versa. You have a text prompt generated and then imposing onto the visual space, and you use that to generate a mask, and you come back. So there are two cycles. We call it prompt to mask cycle and then mask to prompt cycle. And both of them is trying to perform an alignment. So more specifically, you can decompose. In fact, this is similar to the GenSam. So there are multi-hypotheses, but here all the multi-hypotheses are considered simultaneous in a single voting scheme, and so we're generating using a multi-chain here to generating, and then this feeds into this visual contrastive learning. And as a result of that, we perform mask generating, and then we come back generating a voting scheme. So this voting scheme then generating a mask. So specifically here, in the visual contrastive reasoning part, it actually perform a diffusion based synthesizing. So it's trying to hypothesizing, it's essentially perform an impending task. It's trying to synthesizing a plausible object given the prompt generated and use that to vote its agreement with its context. So it's using the context to consider whether the text prompt as a hypothesis can be visually validated. And again, this goes through a ranking process. So those are this is a visualization. There are actual likelihood scores for each of the individual object instances synthesized or impended. So the difference here is we use a lot of different compositions. So the image is divided into a quarter, a half, a quarter, and further, and some further experiment were done. You can also go a random split, depends on how much compute time you've got. So obviously, the more you divide them, it becomes more expensive. And so the objective here is how do we minimize those irrelevant hypotheses and to select and converge onto the more relevant hypothesis. So there are essentially selecting different hallucinations and to make them visually validated. Again, there's a lot more details in the NIPS paper. So if you go in there in terms of how exactly each of the object functions are optimized. In the interest of the time, I will move on to some evaluations. So here are some evaluations. The model performs well for different benchmark tests. This is compared with both different text prompted models and also more recent models using a large language prompting. And this is on different data sets in medical imaging segmentations. All of them is based on a single generic prompt and further test on open vocabulary segmentation. Now, let me move on to the topic of few-shot image generation. So the segmentation examples I used are really to think about how to use large language foundation models. In this instance, is actually large multimodal foundation models to help self-supervised learning. So this whole prompt control learning essentially is a self-supervised learning because there was no label given, and so the model is using the foundation models as a knowledge base to hypothesize both in semantic space, in other words, text prompt, but also in the sensory space, in the visual space, its corresponding features, which can be aligned against those hypotheses. And so the next topic that related, but also imposes new challenges. Increasingly, we actually find we don't have enough data to train models, or the data is imbalanced to extent that we don't actually have a full understanding the degrees of imbalance or bias in the model. And so one of the increasingly emerging trend is, can we use generative models to synthesize data? And here's a particular idea. How do we use diffusion models for few-shot generation? And the model we called CRDI. So first, what is a few-shot image generation? So few-shot image generation is based on the following assumptions and conditions. So you have a pre-trained generator based on a large source domain. In other words, you have a lot of samples. So here's an example of you construct a pre-trained generator. Traditionally, for example, a lot of GAN models are used for this. Star GAN is a good example, but there's lots of GAN models. And in the last couple of years, diffusion models are starts to be looked into. And one of the challenges, actually, diffusion models are much larger in size, and often we don't have enough data. So in fact, often a GAN model performs better. And the objective is that you have a target domain. So you have a source domain, which are well sampled with a lot of training data. And then now you have a target domain. And the target domain, you have only a few examples. And so, for example, here's using facial images as an example. So you have a lot of facial images of adults, and where you have a few images of babies. So the aim is that can you build a model that using the pre-trained model, but with a very few examples, to adapt the model to a new model that can generate a lot of images in this new target domain. So why is this challenging? So for the simple reason, to build a generative model, even using GAN, is very challenging if you only have a few shots. So simply the model will fit, so you don't learn anything. But for a diffusion model, to learn from a few shots, it's almost impossible, because diffusion model even requires a lot more because it has a larger model size with more parameters. So how do we actually perform this task with a pre-trained representation, but with a few shots to adapt? So this is the problem considered as a few shot image generation. So essentially, is actually adapt or generalized to a new domain. This domain has some semantic overlap, but it is also distinctively different. And how do we perform that task? So what is a CRDI? CRDI stands for conditional relaxing diffusion model. So we actually call it diffusion inversion. I will come to that later. So here's a diffusion. So the model considers a, once you have a diffusion model trained, the whole process is in the reconstruct process. So this is not considered in the learning of the noise model. This is once you learn the noise model, how you reconstruct to original images. So in this instance, you have starting from xt, and you going back to the time t at 0, right? And so you're starting with a noise model, and we have this additional model built into the process. And how do we actually then generalize to a different image samples in the new target domain? And the key idea here is what we call a invariance guidance matrix. So we essentially compute a invariance guidance matrix, and this enables the model to diverge into a new target domain using the few shots. So the few shots are not there to build a new representational space. It's really trying to use as an index to guide the model to say where it's plausible to diverge. And using a frozen pre-trained diffusion model. So again, so for each of the time steps from time t to time t minus 1. So this is what it involves. So here's the representation for the Gaussian model. This is the mean, and this is the variance. Okay, so what does this look like? So essentially, this invariance guidance model. So this is what is it almost learns a template. It learns a template how in the diffusion reconstruction process, what's the bound of variation? And that bound of variation for the new target domain. So in this instance, the babies, and starting with adults. So the adults, the bound of variation is very different from the babies. So we're trying to learn what's the bound of variation for the babies in that process. So you would say, so starting from, so you train on my adults, and adults would reconstruct back into adult faces, and by using this invariance guidance matrix, it guides the model to reconstruct to the target domain. So you reconstruct to a baby face. So this is the general idea behind it. So we call it conditional relaxing diffusion inversion. So why the problem is difficult? To estimate the distribution of target domain with a few shots is fundamentally very difficult. We just don't have enough data, so we can't estimate a density function for it. And also, lots of existing models suffer from overfitting because of not enough samples for generative model learning. A very powerful, actually, a model until recently is style transform. So style transform model is actually a GAN-based model. So it learns by fine-tuning and learn a representation by fine-tuning. So you have a few examples, for example, here, different styles, and you fine-tune. This is a GAN-based model based on a pre-trained source model, and you essentially learn adapted generator. And so this is these examples are facial images of real photos, and you want to adapt to a cartoon domain. So the target domains are cartoon drawings rather than photos. But most of those models suffer from overfitting, and the model tend to collapse or suffer from catastrophic forgetting. So, for example, StyleGAN has just under 30 million parameters. But if you're using a diffusion model, and when we're trying to use a diffusion model, it gets really difficult because that's like 3 times more parameters, over 100 million. So, and most of the models currently suffer from very poor divergency. In other words, a lot of diffusion-based generative models, it generates something very similar to the samples. So what we call has very narrow mode coverage. So, for example, those are different. So this is one data set called med faces, and this is the generated results using style transform. So they have a very similar characteristics. It doesn't actually allow for more significant change of characteristics. Another idea is trying to explore foundation models. There are lots of recently lots of foundation models being proposed. Some of them are academic research models, some of them are commercial models, and they all seems to suggest that they can do a zero-shot text-to-image generation or few-shot text-to-image generation, like DALL-E and Dream Booth and text inversion and so on. But actually, most of them are lacking fine-grained diversity. So, due to in the diffusion reconstruct process, there's a regularization parameter, and that parameter is not interpretable. It's very difficult to understand how do you interpret and also control that parameter. So as a result, that parameter it almost like inherently constrain most of those generative processes to be lacking fine-grained details. And the second aspect is those models have suffer from model uncertainty because of hallucination and artifacts. And in order to generate a good visual example, very careful prompt engineering is required. And also the output sometimes is uninterpretable because of the representation is uninterpretable. So here's some examples of if you want to using the text model. So this is using like language models directly, not a multimodal foundation model, but large language models. And this is a good example used by a lot of people to illustrate. So if you say, can you generate a schematic of a diffusion model, and the model doesn't understand what a diffusion model looks like. So it generates essentially a sort of derivative of a nego with some secretary attached to it, because it doesn't understand diffusion model is in fact is a macro statistical process. And here, artifacts are different manifestation of hallucination. For example, here artifacts also medical imaging. There are certain areas that suddenly you have random uninterpretable parts, and same as here, your parts of image are not really coherent with the rest of the image, and so there's lots of generative uncertainty, fine-grained semantic, and resulting in artifacts and hallucination. So why is that the case? I think in a very simplistic way, there are more elaborate way you can explain this, but in a very simplistic way, I think most of the generative diffusion models are essentially, they has a tendency of regress to the mean. So it's a regression process, and it's trying to regress the mean, it's trying to go back to what's most common. So the mean conceptually really represent what's most common. So this tendency of always going back to the most common is the cause of the hallucination is the same, and artifacts is what is when they're during the model training stage, when the source domain, what are the most common aspects. So when you generalize to a new target domain, it pulls away from if you like, out of distribution spaces in your representational space. So a few shot image generation problem is typically set as following. So in this particular instance, we take a source domain using a Flickr faces high quality data. So those are lots of adults facial images, and the target domains are babies, sunglasses, and meta faces. So there are different. So you can say babies are very different from the adults, and the sunglasses are different from most of the Flickr faces, which has no sunglasses. And the meta faces are they are not quite realistic photos. There are a combination of paintings, drawings, and various historical facial pictures. So let's look at how well foundation models can perform. So this is using the source domain, which is the FFHQ, Flickr faces HQ. So if you use that source domain, the target domain are babies. And using one of the foundation models, currently using Dreamboost, it generates all kinds of strange output. And it doesn't look quite real. Same as sunglasses and same as meta faces. And there's another foundation model recently being published called texture inversion. Again, it's not quite natural. So there's a lot of caused by unrealistic, perhaps hallucination, and also which doesn't actually generalize to baby characteristics. So this is another model. So the foundation models, once you apply for them to generate from a pre-trained source domain and then generalize to a few short target domains, they actually don't work very well. So these are real face of babies and sunglasses and metafaces. If you compare those, so all of them have significant problems. But those are actually multimodal foundation models. So visually generate something at least sometimes is meaningful. How about using a large language models? In fact, large language models it's even poor. So using a ChatGPT, if you prompt a text questions, it doesn't actually generate a natural looking facial image. It generates a sort of artifacts. So let's look at a stable diffusion as a good example of a latent diffusion model, and what is the characteristic. So you typically have input, output, you have a pre-trained encoder, decoder, and then you have a diffusion process. So this is fine tuning on a target domain. So typically this is actually when we talk about a source domain. So they are very well sampled. You have lots of training images into hundreds of thousands or millions of images. And then you condition on a large language model to generate a reconstruct process. So this is to learn the noise model and then using a large language model to condition using a unit. Now, the two problems, part of the problem here is in this process, why it's become few shot rather than have a very well-sourced domain, and the model suffers of overfitting. So you can't actually estimate the latent space because most of the latent diffusion models assumes you can learn a latent space in the diffusion noise learning process. But if you have few shot, that assumption is invalid. So you can't learn that latent space. And secondly, the large language model itself, as we just illustrated, often generate hallucinations. So in fact, it violates the few shot learning assumption and principle. In other words, it starts to converge into other populations or other different related domains rather than the target domain. So the idea we're trying to explore is based on a concept called the probability flow correction. So here's an illustration of what a diffusion model process usually happens. So if you have a diffusion model learned from a source domain, when you at a reconstruct stage, the model tend to, because of the regress to the mean, to pull it back to the source domain. So lots of the generated example in the new target domain, if you only have few shots, it's more resembled to the source domain rather than the target domain. It pulls back towards. So this is why one of those baby faces, it looks like a really old baby. So it has a certain baby looking, but has a lot of adults characteristics. But what we actually want is for this model to diverge to the target domain with only few shots. And here's an example in actually how the model learns or progresses in the process of diverging into different parts of the distribution space. So those are the reconstruct divergency process. So let me actually speed up a little bit. So there are two parts, reconstruction. So the idea is, how do we do to convert a unconditional to a conditional diffusion, but without relying on a foundation model? And the idea is to use what we call a probability flow correction. So specifically, we're trying to discover a sample-wise guidance embedding space for per sample, and then we call it invariance guidance matrix. In fact, it's computing a target mean gradient. So the idea is it's almost similar to GAN, So this is using a Bayesian. You have a conditional, so conditional probability, what you want to derive is unconditional, which is a unconditional diffusion model, if you like, and plus a classifier. So that's what GAN has. GAN has a encoding and decoding, but with a classifier to condition it. But in our case, in a diffusion model, that classifier is unknown. It doesn't exist. So the whole objective is how do I approximate this? So the approximation is trying to compute this, what we call a per sample target mean as approximation. And by doing that, we're trying to avoid overfitting, approximate a generative classifier. So the key is how do we approximate this classifier with the processor. So this is essentially say how it's been computed using each pixel is considered the individual instances for that approximation. Just quickly, so this is related to when I introduced it. The key is to compute this invariance guidance matrix. So, and again, this invariance guidance matrix is approximated as classifier. So essentially, we learn a classifier with few examples, and essentially define all the bound variation of a image in a new target domain, how it can change down to per pixel as a Markov process. So again, there are more details in the paper. Given the interest of time, I will move on. In addition, we also extended to from a few shots, for example, 5 to 10 shots down to 1 shot. So the idea of building this invariance guidance, it can apply to individual images as well. So it also works with single image domain diffusion. So experiments the same. We're using with a Flickr faces high quality into 3 different targets, and we're using 2 different matrix, FID, which is very widely used, and we introduced another one called mood coverage structural similarity index measure, and this is specifically trying to mitigate diversity, or to actually quantify diversity, because FID doesn't actually measure diversity. So this example of where diversity, high diversity, no diversity, you can say actually this is the ground truth, and adapted generalization. The upper row you have more diversity, and the lower row you have less diversity, because all the images look very similar in characteristics. So this is just measure the methods, different methods compared with current other methods, either using foundation models or using conditional foundation models. And some of them have more artifacts with lower quality. So you can say those are examples of artifacts. Some of them have less artifacts. And also diversity. The model has more diversity is better. Okay. So quickly to summarize takeaways. So the ideas we're trying to explore is how do we compute test time variance without training, without specific training samples, or with very few, and the self-learning from small data. And the objective from a computational perspective is trying to learn an adaptive mean. In other words, if you like, the foundation model provides it with a mean of your large data distribution space, but we want to learn an adaptive mean for target domain. Often you don't have data, or you don't have labeled data, or you have very little data. And the second aspect is we're trying to explore the idea of using foundation model not to generate the output either for segmentation or for generative process, but for reasoning. So it's not for the reasoning is most of foundation models are good for reasoning, but not really good for visual details at fine-grained detail. So there's a whole bunch of other issues we're trying to emphasize. And how do you avoid overfitting? How do you explore hallucination rather than trying to discard them? And how do we explore a lot of distribution plausibilities, and diversity. I think I should come to a stop.
Okay, thank you very much, Professor Gong. Questions, please. Let me check if there's any question in the chat. No, there's no question in the chat. Are there any questions, please? It seems that our audience is not really very talkative tonight. And since we have already passed is there a question?
Yeah, I actually had a question. If
Yes,
this,
please, go ahead.
yeah. So thank you for the presentation. It was very interesting. I was wondering because when you showed the results of from Mac, I think like the second camouflage segmentation model that you proposed,
Mhm.
it was performing better than Gen Sam. Like
Mhm.
what is the key innovation in your opinion? Like why is it better?
Okay, so in Genzyme, we don't consider multiple hypotheses in this, and we don't actually compute, we don't actually take them all into consideration. So in the Genzyme, we generate multiple channels, but we discount them straight away because it depends on the heat map. So we don't reason. And so in the ProMac, we actually reason all of them. And another aspect, we reason them not in a image holistically. So in the Genzyme, we take the image, we try to compute a visual heat map in the image, and then
Mhm.
we actually consider which one has the highest score. In other words, winner takes all. But in the ProMax, we divide image into multiple parts, deliberately trying to. So, but why we do that? Because we're trying to synthesize part of image without object, because we don't know where the object could be. So we divide it into multiple parts. By doing so, we create possibilities. Some of the images or the sub-images, if you consider compositions of images, which would probably have no object or have a bit of object, but then it's semantically meaningless. Then we're trying to use that to also generate hallucinations. And we don't discount them. More of them, we consider them as in context, what are possibilities? Because sometimes what is possible may not be visually distinct, and sometimes it's not as you like, it's not supported by surrounding pixels.
Okay. Yeah, that's super interesting. Thank you.
So it's almost like we flipped the coins. The Gensan, I think the principle is reasoning positively. Think about validating what's there. The ProMac is reasoning negatively. It's essentially trying to say what's not there, and then say how true that might be.
Okay. Okay. Thank you.
Are there any other oral questions?
Are we going to get the slides or the recording?
The recording, yes. Typically, if you go to the AIDA webpage, then we have all recordings of previous and also PDFs from previous AI Excellence lectures.
Yeah. What is the link to AIDA or I can
That's
access?
how you got this the invitation to join this
I got,
telco. Then in there you're going to find information about AIDA,
yeah,
the International AI Doctoral Academy, and if you go to resources, then under resources you can find the PDFs and the videos of all excellence lectures. So it's a misfit, but Manid already put the AIDA webpage in the chat.
yes, good, excellent, excellent.
Any other questions?
No, thank you very much.
You're welcome. Professor Gong, there are one or two questions in the chat. Please, can you have a look at them?
Okay, let me have a look.
Yeah, there is one about medical images and biometrics and the effect of generative approaches there.
Okay, I see that difference in medical images face metrics using this gender. No, it actually it doesn't. I mean, obviously, okay. So there are different. You need few samples from each of the domain. I didn't have a time to show. In fact, we have some other examples which, this is to do with the few shot generation. We also apply to buildings and cathedrals, and so it's more than one phase domain. So we just use phase. Phase is a very common domain in the community when people use few shot generation, but there are other domains and also equally applicable. The next one. Okay, so that's a very good question. I didn't have time to discuss. We also have some other work on video for video segmentation or video grounding, and we also use the same concept. So what we discovered is foundation models, often people use foundation model trying to either perform generative tasks, in other words, generate data which resemble missing data, or using foundation model to perform to assist discriminative tasks. And again, it's based on trying to explain subtle differences, like attributes or composition of attributes of object. But often, actually, foundation models are very poor for explaining those subtle differences, or what I call fine-grained differences. For the simple reason, foundation models has no ability to perform either spatial grounding or temporal grounding. In other words, know where it is. It knows the nature of most foundation models are weakly supervised contrastive learning. In other words, you have description, you have a visual data. You learn by that weakly pairing. There's no labeled information, which bits of your semantic token corresponding to which parts of the pixels. In other words, grounding. So there's no grounding information in the learning process. So when you use foundation model trying to perform those grounding related tasks, for example, segmentation, detection, classification of multi-instance in a single scene, which intrinsically require you to perform grounding. In other words, where it's not just ask question of what it is, but also answer the question of where it is. And also in video, if you want to do video movement retrieval or video grounding, you need to know when exactly certain things happened. Again, requires grounding information. Foundation models are actually very poor for those type of tasks. What it's good at is providing this holistic context for you to reason about. And then you need other means to help you to make that link, what I call alignment. So you need the alignment between the visual features or signal features, because it can also apply to other domains like in audio and in robotics, which are other sensory data as well. And the context. So you have a context which foundation model can provide a very good, sometimes quite richer context, and sometimes the context may be beyond what's in the scene or in the data or in your images or videos. But that's actually not necessarily a bad thing. You can find a mechanism to discover which other ones are really there, which other ones are perhaps partially there. Maybe it's occluded. So for segmentation or for some other tasks, sometimes objects are not visually well seen. There are only bits of it. In fact, that hallucination can help you to solve some of this problem as well. I hope that answers that question.
Okay, thank you very much, Professor Gong. It was a very interesting lecture, and we had some questions as well. Again, I would like to thank you, all of you, for participating, and in particular, Professor Gong, for delivering this lecture. And since we are almost going closer to Christmas and New Year's vacations, I wish you all the best. Okay.
Thank you, Yanis.
Bye.